So in this second part of this video on regression analysis of time series data, I'll look at how to run a couple of more complicated regression equations, and I'll look at how you can actually test a linear restriction where you can't actually use the f-test or the wall test function, but you can just run it manually. So here I'm going to estimate what's called an error correction model of the second order on my production function. Again, it doesn't matter if you have not done this, you don't understand the econometrics. Basically, it's an equation where you have the first difference of your dependent variable as the dependent variable, and then you have the first difference lag once, you have the first difference of the other two independent variables, and lags of the first difference, and so on. You can see it's quite a complicated lag and difference structure, but as we've seen, using the diff function combined with the shift function, you can easily create all of these lags very easily and differences. Running that, of course, to create, first of all, the y and x matrices, and then running the three commands to get the results. We've done this before. There we have our results. Again, we get this little warning because of the small sample size on the kurtosis, but that doesn't matter here. Now, we saw before how to create some graphs of residuals and so on, which could be useful. I did those all separately before. Up here we had the residuals and then the autocorrelation. What if you wanted to combine them into a single chart, like you can in R with one of the commands in the forecast package? Well, the way you can create a combined graph with subplots, we've kind of seen this before, but this is a slightly different approach. So what I've done here is, first of all, you use this statement here. You put fig dot and then axs, which stands for axes. In matplotlib, an axis is a particular chart or subchart. And then you put equals plt dot subplots, and then in brackets you tell it how many the layout you want. So we want 3 rows and 1 column, so there's going to be 3 charts, and then you put appropriate fig size, and again you'll need some trial and error there to make sure things fit nicely. What this now means is that you can then refer to each separate chart as an axis, an axs variable. That is, as you can see here, if you put axs and then in brackets the index 0, that refers to the first one. Axs and in brackets 1 is the second one, and the ax in brackets 2 is the third one. So you can refer to each separate subplot, each separate chart, by using this notation here, and then you can apply the standard functions like plot and set title and so on. So as you can see, what I've done here, the first chart is plotting the residuals, and I've set the title for that. The second chart is plotting a histogram of the residuals, which we've seen how to use the his function for that, and again I've set a title. The third chart is going to be the ACF, which we plotted before using this function here from stat models. Here you actually put the axs variable here, or indicator, as the value for this option ax in this function. So it's slightly different from these. And then we use plt show to show all 3. And so if I run that, you'll see we get all 3 in a nice combined chart, one on top of the other. Of course, if you wanted a different layout, you could specify that here with individual titles And I think that's quite a nice way of doing it. Rather than doing them in separately, you can put them all in one go, so you can see the results on the residuals much more easily. So this way of creating multi-chart graphs using this fig, AXS, and then equals plot PLT subplots, and then referring to each separate one using this notation AXS brackets 0, AXS brackets 1, and so on, is very useful in matplotlib. So all we need now to do is just run a Bryce-Godfrey test here to test for first order autocorrelation and second order. We've seen how to do this before. If you want, of course, to test for heteroscedasticity, you can run the Prausch-Pagan test. I looked at this in the previous video when I looked at cross-section data. So that's just repeating stuff we've done before. Now, you might want to, instead of testing or estimating an error correction model order 2, you might want to look at an ECM1. So I've done that here. And so this is how you specify that. Again, if you don't know what error correction model is, don't worry. It's just, I'm just using this, but this is the specification. So I'm going to run that and get the results. Here we go. Now, the reason why I've done that is because this enables me to show how you can test a restriction here, which is cannot be done by the ftest function because I think it's called a non-nested restriction. But basically, when you go from an ECM2, an error correction model order 2, to an ECM1, you're actually effectively imposing three zero restrictions. And so I can test that here by running this ftest manually. First of all, I'll look at the autocorrelations tests here. But how would you then run test this restriction from restricting from ECM2 to an ECM1? Say that involves three restrictions. Well, if you know the statistics here, you'll know that the ftest is given by this formula here. It's the residual sum of squares in the restricted model minus in the unrestricted model, and that is then divided, whatever that comes to, divided by the degrees of freedom in the numerator, which is the number of restrictions. I say in this case it's 3. And then on the denominator of this statistic formula, you have again the unrestricted, these residual sum of squares from the unrestricted model, and that's divided by degrees of freedom. I think it's n minus k there. I'd have to look that up, but it turns out to be 9 in this case. If you've done this, you'll know this formula. So we can run this by, first of all, calculating the residual sum of squares in the restricted model, which is the ECM1, and the unrestricted, which is ECM2. And you can see you can easily do that. We know how to get the residuals using the resid property here. So I've got the residuals, squared them, and then found the sum. In other words, the sum of squared residuals. And here for the unrestricted model, and I put those into the formula. And then I'm going to print out that f-stat. Now, how do you get the p-value for the f-stat? When here you need to use an f distribution, and you can get that from this package SciPy and the stats module in that. So you need to run this little command here to import the f distribution from scipy.stats. Now, SciPy, I think, is a standard package available with a Python installation. Obviously, if it so it should already be there. If it's not, of course, you can always get hold of it, of course, via PyCharm, as we've seen. So you need that SciPy package in there. So you run that little command which imports the f statistic, and then the f-stat is given by 1 minus f dot, and you want the CDF, the cumulative distribution function, and then in brackets you put the f-test variable that you've just created, and then comma, first numerator degrees of freedom, comma, denominator degrees of freedom, like that. You can see how I've done that. And that's how you get the p-value. So if I run all of that, you'll see what we get. Here's the S statistic, and here's the corresponding p-value, which is, so the test here is that those three restrictions, they're jointly equal to 0, and that's rejected, suggesting that we best sticking with an ECM2. So I think it's useful to see here how if you're not able to use the f-test or wald-test function directly, you can still run an f-test of a linear restriction quite easily by just running it manually like this. Okay, so that completes looking at the basics of regression analysis of time series data.